Thank you. Testing, testing. 1, 2, 3. So you made it. Good. Anybody have to cross the picket line to get here today? Yeah? How was your experience, sir?
I didn't have to wait too long because I went around like 1 week. But coming into Maine, I saw it was pretty fast.
Okay. Well, for the benefit of those of you who will be joining us later by recorded video, what can you do? Yeah. So, with respect to the whole strike situation, I am not sure at this point in time how many of the TAs for this course, pardon me, still getting over that cold from last week. I don't believe I'm infectious. It's just, you know how it gums up your system, it takes a while to just get it through, you know? That's kind of the phase I'm at right now. I sound a lot worse than I feel. With respect to the situation for this particular course, at this point it is not known to me how many of the TAs for this course have gone on strike or have decided to not go on strike. So I don't know, what level of service cuts will be happening. I don't know if some or which of your tutorials will still be going on. At the moment, while things are being sorted out, probably if I do have any TAs who are remaining, I'll have them do a recorded tutorial session so that everybody can watch it in post. Because, I know some people have tutorials later this morning, and I don't know if we'll have any TAs there or not, but it is what it is, I suppose. Any questions about anything pertaining to anything of it like that before we get moving? Yes?
Are we still going to be getting our physical tests back?
Oh, yes. Yeah, you're going to still be getting the physical tests back. Oh, shoot, I forgot those at home, didn't I? I was going to distribute them during office hours today, but what with the strike and my wife had to drive me into work, which meant we had to load all the kids up, and Felix was still in his PJs, and I just forgot to bring the tests with me today, so I apologize for that. I'll get you your tests this week for sure. No later than Friday after class. Okay? Any other questions? Did they post the assignment 2 grades before they went on strike? For some people? All right. Great. All right. We'll sort it out. It might take me some time. Basically, the prevailing wisdom at this point is that everything that you expect to happen is going to happen probably, but just who the hell knows when. That's sort of how it's going to go. Because I got to do everything myself now. Between my 3 courses, I have 13 TAs, which is the equivalent of 4 full-time staff, plus a little bit extra. So, if all of them are on strike, which I imagine, they probably more will be on strike than the university would like to think are going on strike. It's going to gum up the works considerably. So, I beg your patience, but I think in a couple of weeks' time, everybody's going to be losing their patience. So, at any rate, strike. Okay. In addition, one brief announcement. I'm going to be ending the class today about 10 minutes early. My next class, I'm actually being interviewed for a full-time position during the lecture, so I need to be there on time, so we'll cut right to the chase then, and we won't waste any more time, eh? Okay, cool. So, we've been talking about digraphs, or directed graphs. Very brief review. Where's my little laser pointer thing? There it is. So, all right. So, directed graphs. In concept, not very difficult to understand. We simply take the edges of an undirected graph and assign direction to it. Another way of saying this is that whereas previously we described the edges between two vertices as being a pair of vertex indices, and we did not care about the ordering of said indices, in a directed graph, we do care about the ordering of these indices, right? They no longer just indicate an edge between these two nodes. They indicate an edge from this node to that node, right? Although we started off with undirected graphs can actually be described by directed graphs, but not vice versa. A undirected graph is a graph in which all edges are bidirectional. So far so good. Our representation of the graph inside of Java or whatever other programming language you happen to be using, very similar to the manner in which we encoded undirected graphs. The primary difference being we're only recording half of the numbers inside of this array of lists, right? When you access any particular vertex in the adjacency matrix, again, can we call it a matrix? Adjacency list? Array of lists is just so clunky, you know? But anyway, when we access any of these indices, we get all of those indices which the selected index points to. Whereas for, we would have, if we had an edge between 4 and 5, if we looked up 4, we would get 5, and if we looked up 5, we would get 4. But you'll notice in this case, 4 does not lead to 5, because 5 leads to 4, and not vice versa. So, basically, that degree of redundancy has now been removed. We no longer consider, we've basically broken the bidirectional relationship of adjacency, right? 5 has 4 adjacent, but 4 does not have 5 adjacent in this context. Does that make sense? With me so far? Yep, good. Incidentally, inside of a directed graph, you are still permitted to have bidirectional edges. Whether you choose to model these as two separately instantiated edges, one going one way, the other going the other, or if you choose to put a modifier on an edge to say this is bidirectional, the way that it's handled here, it models it as two separate edges going in one direction and the other, because that's easier to integrate into our array of lists representation. But this is, of course, not the only way of representing a directed graph. It just happens to be an efficient way of representing a graph. You're perfectly welcome to use inefficient ways of representing it, just not in this class. Good? Good. So, let's get that. So let's discuss applications of our two searching algorithms, which we have discovered, to the directed graph as opposed to the undirected graph. We developed the concept of depth first and breadth first search in the context of the undirected graph. It turns out that the depth first search, particularly in undirected versus directed graphs, is actually the exact same damn algorithm. Like, to the point where if you take this bit where we are, like if you add this line and maintain an edge to array inside of this DFS algorithm operating over a digraph, you have the exact same code to the character. So basically, depth first search is a digraph algorithm, and you know, we can use it freely and unconstrainedly on digraphs without having to perform any modification of it whatsoever. Question?
If the two algorithms are the same, then can you please explain what is H2 line doing in the first algorithm?
Yes. So, in order to answer that question, we should take a look at what edge 2 was keeping track of in the first place, right? So, where was it here? This is breadth first search. So, the purpose of the edge 2 array was to generate, do you remember how we encoded trees way back when we were doing union find? We encoded trees as an array where each index held in its value another index that it's pointing to. That's what the edge 2 array generates by construction over the course of the algorithm. If that's useful to you while you're doing the digraph version, then you should keep it. But if that's not useful to you, then you can dispense with it, because it is basically it's just we're holding some intermediate results so that we can extract the sort of spanning tree without having to write a separate algorithm for it. Does that make sense?
Yeah.
Good. Any other questions? That was a good question. Okay. So, depth first searching a digraph example. Once again, we will be starting at 0 as is usual. Of course, please don't confuse this as being the only possible starting point. Of course, any of these searching algorithms can start from any vertex in the graph. It's just that the textbook annoyingly consistently chooses 0 for everything. I wish that the textbook would mix it up a little bit so as to break the implicit assumption that students may get that you always have to search from 0 because the textbook always searches from 0. Not the case, but you know, it is what it is. I guess that's why they have professors to tell you that sort of thing, right? Otherwise, your education would consist entirely in reading textbooks. So, searching this diagram. Starting at 0, we look up in our adjacency matrix the number 0. We find 5 and 1. 5 and 1,
0 gets marked, we proceed with 5. 5 finds 4. 5 is marked, we proceed to 4. 4 finds 2 and 3. 4 finds 2 and 3. 4 is marked. 3 finds 5 and 2. 5 is already marked, so we skip it, and we go to 2. There we go. 2 checks 0 and 3 and finds nothing. And then 2 is finished, 3 is finished. 3 must check 2, 2 is done, 4 is done, 5 is done. We called depth first search on 1 because we sort of circle back to our first decision that we made, and 1 is not yet marked, so we mark it, and then everything is finished. You may notice that while the depth first search has completed completely, it has not created a tree which encompasses all vertexes in the graph, right? We are going to, as we develop this topic, towards the end, we're going to introduce a new concept, that of the connected component. This guy right here, you may consider him to be a connected component. Pardon me. Although again, we're going to develop that idea somewhat further along. Make sense? Question?
If you're doing depth first search and you have to graph relative to a root node, is there multiple graphs that can be formed or only one graph?
Oh yeah, certainly. There's still multiple graphs that can, there's multiple trees that can be formed, absolutely. Yes. Consider, if you will, the following graph. Right? The tree that you will end up with will either be 0, 1, oh, what am I getting? 1, why am I using a small piece of chalk when I don't have a nice, shiny, really big one? Jeez. It'll either look like this, or 3 and 4 will be attached to the 2. It depends on, in the adjacency matrix, whether 1 or 2 is presented first in the list, and that's an arbitrary decision. That's an arbitrary choice, right? So yeah, in a directed graph, absolutely, you're still in a situation where there are multiple correct trees depending on how the adjacency list is formulated, right? Now, if I were to ask you on a test to produce the tree corresponding to a depth first search over a graph, just for the sake of argument, I would provide you with the adjacency list, and I would expect you to go through it in the proper manner, doing the adjacency list in order, and I would expect you to come up with a correct tree. I would expect everyone to have the same answer, right? Make sense?
Yeah.
Question?
So in that case, like for example, we have this graph. It will be displayed separately into 2 different parts, right? Because the right section of the graph is not presented.
Mm-hmm.
In the test, will we have the like similar questions?
You may, yeah. If it's a directed graph, then
Okay, then which part of the graph should we give?
well, I will certainly tell you which node to start on. That's fair, right? And then the rest of the components of the graph that you will have in your tree are simply those accessible from the starting node.
Okay.
Make sense? Question?
So like all the lists, like choose like that five is first, you always choose a greater, you always choose like a smaller number?
Just in the order they appear.
Oh, okay.
Yeah.
Okay. And then if we were making one of those lists, it's just like an arbitrary choice of which one you put in first?
So in practice, this decision is made during construction, right? So if we remember our facts about linked lists, what's the runtime of insertion into the head of a linked list?
Constant time?
Constant time. What about the tail?
Here?
Yeah. So where are we inserting head or tail?
Oh, head here?
Yeah. So as we add edges to the graph, those edges will be plunked at the front of these adjacency lists because that's more efficient. And so, essentially, the order in which these nodes will be searched under depth first search it's like a stack almost, but it's on the order in which the things were added in the first place, which is of course arbitrary. You can represent the same graph adding the edges in basically any order you choose, right? And it, does that make sense?
Yeah.
Yeah.
Thank you.
Cool. Any other questions? These are really good questions so far. Yes.
So the DFS is a recursive algorithm. Let's say you're on the 5. Once you return, so you're on the node 0, and you went down the path of the 5.
Mm-hmm.
After you recurse back up, you just go to the next. So you maintain the position where you were at 5, and you just go to the next node in the linked list, right?
Yes. So, with respect to item 0, you mean? Yeah. Basically, you can think once DFS 0 is called, the first thing it does is looks up which numbers it's adjacent to that it needs to search. It stores those, and then it goes through them in order. So, of course, it's going to open up 5 first because 5 is first, but if you notice when we get down here to 5 being finished, it then proceeds to open up DFS for the next one, which is, in this case, 1, right? So yeah, it's a little bit sneaky. As I said last time, or at some point previously, basically the only difference between the depth first search and the breadth first search is how you're storing the nodes that you're, in both cases, you're adding nodes to a queue, right? The question is that a FIFO queue, or is it a LIFO queue? Is it a stack or is it a queue, right? In the case of the depth first search, it's a stack, because the first node that you, at all points in the algorithm, the node that you search next is the one that was most recently added to the stack of nodes that you're searching, right? Whereas, with the breadth first search, the node that you're searching is always the least recent node that you've added to the list of nodes to search. Make sense? It's a little bit deceptive because in the case of depth first search, you can, if you formulate it as a recursive algorithm like this, basically you get the system call stack to act as a stack, if that makes sense. So it's like you're overloading the system call stack itself with the stack functionality required for the depth first search to work, right? Make sense? Whereas in the breadth first search, your system doesn't exactly have one universal FIFO queue where it keeps function calls for you to be able to just, put all of your function calls in a queue instead of a stack. Otherwise, we would just do that in that case as well, right? But yeah, because the system has this great big glorious stack that's highly optimized that everybody loves using, that's how they're choosing to do it. Now, that being said, if you're worried about exceeding, if you're working on a very large graph, right, and you're worried about exceeding your system's call stack size, if you're worried about stack overflow, it is absolutely like 100% possible to do a non-recursive implementation of the depth first search. Just substitute the FIFO queue in breadth first search for a stack, and everything will still work. You might have to like tweak one or two little things, but everything will work reasonably, like pretty much exactly the same way. Make sense? Any other questions? Yes, sir.
So would this whole graph be considered a connected component or just a subset?
So we have slides on it coming up, but the Coles Notes version, we're not necessarily concerned about connected components, but strongly connected components. So we're going to introduce a new definition for what a strongly connected component is. It's basically any portion of the graph in which a cycle exists. So in this portion, you can return to 0 from the 2, right? And that gives you a strongly connected component. It's a little bit different from the depth first search, because in theory, this depth first search could migrate into other strongly connected components. You know, if you can imagine if 4's arrow here was reversed, it would search through other connected components. But in general, if it's stopped, it's going to be stopped at the barrier between strongly connected components. Does that make sense? Cool. Any other questions? Good. You guys have awesome questions, I have to say. So, some of the more intuitive of you in the crowd may have already guessed that if depth first search applies to digraphs with virtually no modification, then the same is probably also true of breadth first search. And you'd be correct. Every undirected graph is a digraph with edges in both directions. Breadth first search is a digraph algorithm. Proposition: BFS computes the shortest paths, fewest numbers of edges, from S to all other vertices in the digraph in time proportional to the number of vertices plus the number of edges. Remember, V and E are sets, and that the two vertical back bars on either sideways set designates the, what's the word for it? Cardinality. Thank you. That was being pedantic about set theory moment. So a sub-problem of the shortest path problem, or a different flavor of that particular ice cream, is the multiple source shortest path algorithm. So multiple source shortest path, given a digraph and a set of source vertices S. So we're no longer talking about a single source vertex. We're talking about a set of source vertices. That is to say, for some S subset of V, find the shortest path from any vertex in the set to each other vertex. So, for example, in this graph, let's say our set of vertices is 1, 7, 10. And we are trying to find the shortest path to some other vertex. So, in case there's any confusion about this, our input and output, or our starting and ending vertexes, are still separately being defined, right? In this case, we have multiple source vertexes and one sink that we're trying to find. Basically, we're trying to find the shortest of all of these paths
to the particular vertex where it is today. So, for example, let's imagine we're going from 1, 7, or 10 to 4. 4 being right here, 1 is here, 10 is there, 7 is here. So, path from 1 to 4 cannot possibly exist because 1 has no adjacent nodes. 7, you can go through 6 to 4, which is something you would have to find out using breadth first search, of course. And for 10, you can go 12, 9, 11, 4, which is a longer path. So in this case, the solution would be 7 to 6 to 4. So the shortest path is 2. Make sense? This isn't too bad, right? Shortest path to 5 in similar fashion, 5 being right here. Once again, 7 gets there first. 10, you have, because it's got the extra overhead of having to go through here, like 10 would go 12, 9, 11, 4, 3, 5, which is longer and not as nice. Shortest path to 12, of course, would be 10, but that's kind of, that's making it too easy for 10, in my opinion. He's got to work harder for it, but yeah. So, how to implement? Using breadth first search, of course, we initialize by enqueuing all source vertexes. So, like your intuitive way of going about this problem was probably something like, okay, I keep an array or a list or something with all of the source vertexes that I've received as input. I call the breadth first search on each of them in turn, right? 3, or in this case, 3 separate invocations of the breadth first search, right? And I modify that algorithm, I modify breadth first search so that when it finds the thing, make it into an actual searching algorithm so that it's actually looking for a particular element and not trying to generate a spanning tree. And when it finds the element it's looking for, it returns the distance to that element, right? So slightly modified breadth first search. It turns out that you don't actually have to perform 3 separate invocations of the breadth first search. All you have to do is add all of the source nodes to breadth first search's FIFO key, right? Which is essentially what you're doing anyways, right? In the first version that I described, where you call breadth first search 3 times and pick the minimum, pardon me, we're actually doing more work than we have to do. We're generating information about how every path, every node eventually will find the node we're looking for. But if the breadth first search algorithm is already returning the minimum path, if we initialize it at multiple points, then we can find that the answer will be the answer we want, and we don't even have to worry about this extra information that would have been generated by multiple breadth first search invocations. Make sense? To some degree? Question?
What would the algorithm do in the case of one where it's not connected to 4 at all?
One that's not connected to 4 at all? Like 1 in this example? So none of the source vertexes actually connect to the vertex we're trying to find the shortest path to. Most likely you get some kind of negative answer. A failed, like whatever your programming language tends to do in the case of a failed search, that might be raising some kind of exception. That might be, in Haskell, that might be like returning a nothing in a maybe, a maybe monad type. It could be returning a none. Maybe in Java, what you want to do is return a null or an Python none. One of those types of results is what you would do in the case, because the destination is unreachable. So that's an error state, basically. Make sense? Any other questions? Yes?
If we include multiple source nodes for the BFS, then don't we end up with like multiple trees as well?
Yeah, this is not, you no longer gain the ability to generate a spanning tree if you're doing it this way. Yeah, that's broken. Just for the sake of interest, right? Let's say, I'm going to do a comically simple graph that illustrates my point. So this is a start, this is a start, this is a start, and this is the termination point, right? While this is like a very, very cherry-picked example, shall we say, still a valid graph and still a valid demonstration of what I'm talking about here, right? So, you enqueue these three guys, right? This guy finds this one, he travels here, right? This one finds this one, travels there. This one finds the thing we're looking for and then returns the number of times that, the distance. There's no real correspondence here between a spanning tree, and the best you could do for a spanning tree would be like this branch here, that's the longest spanning tree. This is a spanning tree, this is a spanning tree. They're no longer trees because they're not connected at all anymore, right? So you lose that, but this is a variant on it. Make sense? Any other questions? Ooh. Yes. Yeah, you gotta raise your hand higher.
How does it keep track? Like for this source node has traveled this many, and this source node has traveled this many.
How does it keep track? Right? Using the edge2 array, right? So the edge2 array, right? Once the edge2 array has been generated, all you need to do is look up the destination node in the edge2 array and count how many steps you have to step back to return to any source node, and that gives you the depth. Make sense? Cool. Assuming you're keeping such. Yes?
Assuming we can reach, like in a graph, we can reach to at every node, can we find, is there a way to find source vertex, like a set of source vertex?
No, that's given to you by the, there's nothing, a source vertex isn't necessarily a vertex with nothing pointing to it, or nothing pointing to it, right? What you're looking for there is nodes with an outgoing degree or an incoming degree of 0. But this is again, if we consider this example, 0 does have stuff coming into it, despite being a source vertex. There's nothing particularly about the way that a graph is configured which designates some nodes as being source nodes.
that's a decision that's made by the programmer, or the, that's consequent to what you're using the graph to model. Make sense?
Yeah, I was thinking like we could, we could find the strongly connected components.
Mm-hmm.
And then the set of all vertices inside the strongly connected components, we can have any one of them be the source vertex.
Yeah, again, it'll be something that's sort of given to you by your situation. All right, folks, I gotta get moving, so I apologize for cutting class a bit short, but thank you very much for your time and attention, and I'll see you on Wednesday.